Okay, so we have one more motion problem that we want to look at, and this is probably the most complex that they're going to get. I'm going to do it with the motion equations, and then I'm also going to do it with a motion graph. And you'll see that actually, in the case of this problem, the motion graph can actually be an easier way to solve this than with the equations. So let's start with a sketch, though. We have Carl riding his bike. Um, sure, something. Uh, yeah, sure, that's a bike. Carl riding his bike. We have Nina riding her scooter. Um, Probably that hand should be going this way. There we go. Now she's holding onto the scooter. Nina riding the scooter. We know that Carl is going at a constant 10 meters per second, and then Nina is going to be accelerating at 4 meters per second per second. And the question is, we want to know like if they if she's starting at zero, we know that her initial velocity is zero. Then how long will it take for her to catch up to him? So now we need a coordinate system. Let's say at this point, right when Carl passes Nina, we're going to call that zero, and anything going that direction positive, anything going that direction negative. All right, great. We have our coordinate system. Now we're going to need some variables. But we have to be careful here because in addition to the kinematic equations only being able to handle uh, a single dimension and them only being able to handle a single constant acceleration, they can also only handle a single object at a time. So they're pretty limited in a lot of ways. But the limitations, again, are you have to have constant acceleration, you have to have one object, and you have to be moving in one dimension. As soon as you break any of those rules, you can still use the kinematic equations. You just have to use a new equation each time you break the rules. So if I had two objects, I have to use two sets of kinematic equations, which means I'm going to need two sets of variables. So let's go down the list with those. X naught, or X naught, X, B naught, V, A, and T. We'll do this for Carl, and then we'll do a separate list for Nina. She'll have X naught, X, V naught, V, A, T, do, 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 do. And then we can start going through and solving it. So we know that they are both starting at 0 meters. We don't know um, how far they're going to get. And in fact, that's actually the question that we're wondering. We want to know how far they'll get. We know that Carl's initial velocity is 10 meters per second because he's doing that at a constant rate on his bike. And we know that Nina is starting at 0 because she's just standing around waiting for him or whatever she was doing. This isn't that important, but Carl's final velocity is 10 meters per second as well because he's going at constant speed. Nina's is unknown though. We know she's accelerating, so it won't still be 0, but we don't know exactly from the problem what it will be. Carl has no acceleration, whereas Nina has an acceleration of 4 meters per second per second. And then last one is time, and we don't actually know how long this is going to take. That's a question mark for us. So now we have to go down the list and figure out which equation we're going to use as we go into our solve column. And I'll tell you that a fact to know, something to keep in mind, is that if you want to figure out how long it takes for one object to catch another object, or if you want to find how long it takes for two objects to hit each other, you have to find the moment in which they have the same time or the same position at the same time. If you're in the same position at the same time, you hit. If you're in the same position at different times, you just happen to walk through the same spot. And if you're in the same time, you just happen to be everybody who's existing in the same period of time at the same time. So it has to be same position at the same time. So since we're trying to force that to be true, we're going to have to use an equation that has position and time in it, which brings us to our second kinematic equation. So I can set one up for Carl and Nina. I'll have Carl one, and I'll do Nina's below just so I have space to write them out. Carl is going to be x equals x naught plus b naught t plus 1/2 at squared. Nina is x equals x naught plus b naught t plus 1/2 at squared. But as we go through here, we have to use correct Carl variables and Nina variables as we go through. So Carl, we don't know what x is. We know x naught is 0, so we can get rid of that variable. We know v naught. We don't know t, but we might find that out later. And let's see, we know that Carl is not accelerating, so his acceleration term's also 0. That means that I can simplify his equation down to x equals v naught t. Then for Nina, Nina's side of the bargain, such as it is that we know that she's starting at 0 as well, and she has no initial velocity. So hers will simplify into an equation that looks like this: x equals 1/2 at squared. Now, if we want them to hit, that means they have to have the same x, which means we can get away with setting these two equations equal to each other, because if x equals x, then v naught t equals 1/2 at squared. And now we can start doing some fancy algebra, because we know that this t will cancel with one of those t's. And if I want to get t by itself, I could say 2 times v naught over a is equal to t, or 2 times 10, that's 20, divided by 4, it's going to take 5 seconds. Okay, if we know it takes 5 seconds, now we just have to go back to one of the equations and plug it in. I'm going to plug it into the first equation here. The x equals 5 times, 10 for the velocity times 5, and that's at 50 meters. So we got this was 5 seconds for there, and we figured out that this was at the 50-meter mark is where Nina catches him. So Carl does not get to be a winner for very much longer. As soon as she catches him, once your daughter beats you, you're a loser. So sorry, Carl, you're a loser. All right, thanks for, oh, wait, I'm not done yet because I wanted to show you guys some Motiongraphy stuff. This is from a past video, so oops, let me get that out of the way. Let's do this with the motion graph real fast. I'm actually going to do this with the velocity versus time graph. For the velocity versus time graph, I'm going to extend pretty far over, and I'm going to give myself a real scale here, where I'm going to, I'll do 10 seconds, even though we actually know that it's going to take less than that. But let's do 10 seconds, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good enough. And we're going to do velocity on this axis and time on this axis. And so let's do Carl first. Carl's going to be red. We know that Carl is going, I'm going to put right there, 10 meters per second. And he's going at a constant 10 meters per second. So I'm going to even extend that past the 10-second mark. Just going to go all the way across. Now here's what we know for his daughter. We know that she is going to be accelerating at a rate of 4 meters per second, which means that by the time that she gets to the 10-second mark, she'll be going 50 meters per or 40 meters per second. Did I just math right? Yeah, 10. So 10, 20, 30, 40. She'll get up to here. She'll be going 40 meters per second after 10 seconds. So I can draw, oh, that's not great. This only works if I do a decent enough job on drawing a straight line. Still didn't work out great, but let's just try it one more time, and then we'll just say that's the best we're gonna get. Hey, that was pretty good. Okay, so we have those two lines. We have Nina accelerating with a slope of 4 meters per second per second. We have Carl that's going to constant 10 meters per second. Now we just have to figure out when Nina catches up to Carl. And we can use the graph for this because the displacement of a velocity versus time graph is the position, or the area under the curve. So I just have to find a spot where the area under the curve is equal for both of them. And that happens, you can even eyeball it, hopefully. That happens right here. Because right at this time here, Nina has this little triangle above the line and this little triangle below Carl's line. But if I put that triangle there, they would be the exact same area. So right here at the 5-second mark, Nina and Carl have gone the same distance. And you can see that Nina is going much faster than Carl is at that time. So she's just going to pass him at that point and keep going. So this at the 5-second mark is right where she catches him, and she's going past, and he's turning into a loser. So that's how you do that with the motion diagram, or with the motion graph. And the AP exam is probably going to have questions that have you prove stuff with a motion diagram and then also look at it with equations and talk about how they reinforce each other. So this is a question that kind of demonstrates some of what you would do for that. So thanks for watching, and I'll see you in class tomorrow.